All right, we're back for our next RC circuit video, and in this one I'm going to show where those exponential functions come from. The exponential functions are not given on the AP formula sheet. Now, of course, this year the test is open book anyway, so you'll be able to look them up if you want to. But they very well might still ask you to do something like show where they come from. It involves a differential equation, so I'm going to show you how to set that up. And I'm going to do the discharging capacitor case first. This is the same circuit diagram that I had in the other video, but I've thrown the switch over to the right already. So I'm saying that the system was charged, so Q has some initial value, Q naught. But once the switch is over to the right, it's going to start discharging. So I'm going to draw some pluses and minuses on the plate. I know that the top plate is a positive one based on the way the battery was facing. And I know that the current is going to flow clockwise, in this case, while the plate's neutralized. So the way to come up with those exponential functions is to write a Kirchhoff's loop rule. So loop rule. And the loop that I'm going to use is the same red arrow that I just drew, basically. So I'm going to go in the direction of the current. And there's only two objects in the loop. So I know that the total delta V is 0. The delta V that I would write for the resistor is negative IR. And I used a minus sign because I'm going in the same direction as the current. Again, when you're writing out potential differences, if you pass through a resistor in the same direction as the current, it's a negative term. And then I also need a term for the capacitor. Delta V for a capacitor is Q over C. And that just comes from rearranging the definition of capacitance, or the Q equals VC formula, if you want to think about it that way. I'm not writing Q naught because I want this loop rule to apply at some arbitrary point in time, not necessarily at the beginning. It's more general than that. So whatever Q is at some moment in time, and whatever the current is at that same moment in time, this condition always has to be satisfied, even though Q is changing and I is changing. There's this relationship between them that has to always work. And the trick here is that Q and I are related to each other because you may recall the definition of current involves a derivative of Q. Current is charge per time. It tells you how much charge flows past a point in a given amount of time. So that I can replace. And you might initially think that all I have to do is write dq dt, but the Q in this particular problem has a very specific meaning. It's not just charge flowing past. Q specifically means the charge of the positive plate in the capacitor. So in this problem, Q is a decreasing quantity, which means dq dt would be negative, but I am going in the same direction as the current, so the current should be positive. So instead of writing dq dt, I need to write negative dq dt. Negative dq dt is going to be positive, just like I should be positive. So with that minus sign in place, everything is going to be internally consistent. And then I can write this other term, the plus q over c. I can rearrange. So dq dt times r is negative q over c, or dq dt equals negative 1 over rc times q. So this is a differential equation. Q is a function of time. This equation is relating that function q to its own derivative dq dt. This is not an equation that you can solve through separation of variables. You just have to know the solution. But what the equation says is that the derivative is the original function times a constant. And that constant is negative 1 over rc. So the function, which you can take a derivative of it and you get the original function back times the constant, is e to the x. So I can tell from this q of t has to be q naught times e to the negative t over rc. That function satisfies the differential equation that I found. So q naught is just the initial value. The negative t to the rc means that as t increases, the function itself decreases. As t goes to infinity, this function goes to 0 asymptotically. And the rc needs to be present in the exponent also, so that when you do your chain rule part, you get that constant, the 1 over rc, that was present in the differential equation. Now, having figured out q of t, I could figure out some other stuff too, like the potential difference. I should write of t. The potential difference of the capacitor as a function of time should be q of t over c. So that means delta v as a function of time, it's going to be q naught over c times e to the negative t over rc. And q naught over c I could also write as delta v naught, if I felt like it. If I was interested in the current as a function of time, I can get the current by taking the derivative of q. So if I take the derivative of q, q naught is still going to be there, e to the negative t over rc, and then in the chain rule, I get the negative 1 over rc. And that's exactly what I expected, given that that's what the differential equation further to the left already says. Okay, so that's the discharging case. In the charging case, let me draw the switch. This time the initial charge is just 0. So I'm going to do a loop rule again. But I have 3 elements in the circuit now. I've got the battery, as well as the resistor and the capacitor. So the loop rule is going to read E minus IR minus Q over C. Notice the capacitor term is negative this time because I'm moving from the plus plate to the negative plate. So V is decreasing when I go through the capacitor, so I need a minus sign on that term. I can again replace the current with a derivative. This time I don't need that extra minus sign because in this case Q is an increasing quantity, so dQ dt is positive, just like I need I to be positive. So the solution this time is not as easy to see. So I'm just going to write, I'm going to isolate the dq dt. Looks like this. I think I did that right. Yeah. So the first term is constant. But the second term still has that Q in it. So again, the solution for this one is not as easy to see, but it does lead to that form that I showed you in the other video. And it's easy enough to check this, even if you wouldn't come up with it on your own. So there's going to be some maximum Q value, which you can think of as almost like an amplitude or coefficient in front. And the real action goes on here in the parentheses, and it looks like that. So, again, your test this year is open book, so there's no need to like memorize this form, this 1 minus e to the negative stuff form. But it would still be useful to be familiar with it. The decay function is easy to think about. It's just e to the negative x, essentially. But the growth function is 1 minus e to the negative x instead. So that's Q of t. If I wanted, I should go back to black. If I wanted delta V of t, just like in the discharge case, all you have to do is take the Q function and divide it by C. So I'll have Q max over C times 1 minus e to the stuff. And Q max over C is the same thing as V max, delta V max. And if I want the current, I just take the derivative of Q instead. The interesting thing to note, though, is that when you do take that derivative, since there's two terms this time, that first term is constant, right? If I distribute the Q max, it says Q max minus Q max times e to the negative stuff. So the first term goes away when I take the derivative, which means that the current is just going to be, it's going to end up being in the decay form again. I'm just going to write I max. Oops, I need the parenthesis. E to the negative t over RC. So Let me try to justify that. So I'm gonna clip that out, I guess. What I need to do is take d by dt of Qmax minus Qmax e to the negative t over RC. So again, the derivative of that first term is just 0. The derivative of the second term is going to be Qmax times e to the negative t over RC. And then I do chain rule, so I have to take the derivative of that exponent. And the derivative of that exponent is negative 1 over RC. So the minus sign in front of the term and the minus sign in that chain rule constant, those are going to cancel out. I have the exponential factor, and then I have Qmax over RC. Qmax over C is equal to the EMF of the battery, because if the capacitor is at its maximum charge Q, that means I know that there's no current flowing, and that means the potential difference of the capacitor must equal the potential difference of the battery. So again, Qmax over C, which is the voltage, has to be equal to E. So I've got E over R, but that's current. E divided by the resistance is the current you would get if the capacitor weren't there, which is the same thing as the initial current, or the maximum current. So the Q and the RC stuff, that's all there. It turns into the maximum current. Okay, so that is it for this one. I'm going to do, I think, 2 more. I'm going to make another video about the time constant, and then a final shorter one with a different example circuit.